the need to move water from point A to point B, particularly uphill, has been a need for thousands and thousands of years. I think you understand that. Your study of history, you've got a good handle on the need to move water around. Of course, in current day, you're very well aware of our need to do that industrially for heating, ventilating, and air conditioning. And so let's just say moving liquids all around. And so we do that by way of pumping. And so pumping is a category of equipment. Pumps are categories of equipment that mechanical engineers are faced with analyzing over and over and over again. Almost no matter what type of mechanical engineering you go into, you're going to find that you're going to be wanting to pump a liquid from point A to point B, and you need to find out, well, how much power is it going to take to accomplish that task? So I've created a couple of example problems and a little bit of a crash course to show you how to determine how to analyze a pumping situation. Pump computations. So what I want to do first is want to give you a quick crash course. So rather than just assuming you've mastered a couple of things, assuming you've mastered your understanding of how to handle incompressible fluids, okay, and then also how to determine the reversible work, W dot over M dot, for an open system. Let's do a little memory refresher on those two critical points before we get into the example problems. And then I'm going to show you two example problems. They're different pumping situations, but the easiest will be SI units. And then the more difficult is going to be a pump analysis in English units. Now, if you go out and get a job somewhere in the United States, you're going to be faced with doing pumping problems. Nearly 99% sure your analysis is going to be in English units. So here we go with the crash course first. Okay. This is what an industrial centrifugal pump looks like with a supply water or liquid coming into the eye of the pump. Okay, this is a centrifugal pump, so there is an impeller inside here. More details in just a second. It's spinning around and it's being driven by an electric motor through this shaft, hard coupled shaft that's driving the impeller. And that impeller is serving to increase the pressure of the water so that the outlet pressure with this liquid being supplied to some industrial process is at a higher pressure than the inlet pressure. And that's basically the idea of a pump. That's what a pump does. Here's a cutaway view of that centrifugal pump or something similar. I'm showing the water or liquid going into the eye of the rotating impeller. So you can see that here's the shaft drive being driven by, say, an electric motor. Okay? And then the outlet water is collected in the outside, the casing of the pump, and is discharged through one single discharge out to the process. Here's what the impeller alone of a centrifugal pump looks like. So we've got the ingoing fluid going into the eye of the impeller, and this impeller is spinning around with backwards curved blades. So that's essentially the design of the pump. Mechanical engineers spend careers designing the shape of these pump impellers for maximum efficiency. Okay, so this impeller is spinning around, and so I've tried to depict what's going on with the liquid. It's going into the eye, and then it's being slung out through centrifugal forces to the outside, increasing the kinetic energy of the fluid as well as the pressure of the fluid. And so as this water is slung out to the outside of the casing, then the water is sort of collected into the casing and then collected for a single discharge, the single discharge connection that goes to the process. So I hope that gives you a little better idea of what's going on inside a pump. Okay, now a little bit of the crash course about what is an incompressible fluid. So let's think about just the definition of an incompressible fluid first. Think back to I think it's probably your first week of thermo class. Incompressible, that means rho is constant. It means the density of the material, incompressible. The density doesn't change, it's a constant value. That must also mean that the specific volume is constant. Rho is 1 over specific volume. The volume can't be decreased anymore, no matter what pressure you put on it. It's incompressible, constant density, constant specific volume. And here's a great example for me of an incompressible fluid. It's a bucket of water. So how about a bucket of water? So any liquid that is either a saturated liquid, falls on the vapor dome, or a compressed liquid to the left of the vapor dome is considered to be an incompressible substance. So I'm trying to depict this on a vapor dome associated with the TS diagram. And so put that in the back of your mind visually, that anything to the left of the dome or saturated liquid on the left part of the dome is considered an incompressible substance. And this is where we've tried to pump materials. This is where we pump liquids. Okay, crash course is getting near the end. Remind yourself, what is the work for an open system? You have a pretty good handle of the work for a closed system, don't you? A piston and cylinder, work is the integral of PDV. And for the closed system, piston and cylinder, think of the units of work for a closed system. Don't you normally think of that as kilojoules? Well, the work for an open system is not kilojoules. The work is defined, so I'm jumping down in my slide. The work for an open system is W dot divided by M dot. It's the power divided by the mass flow rate. And so this applies, so little w applies basically to one inlet and one outlet, steady state, steady flow, okay? W dot over M dot. And so here's the first law. Here's the first law with no change in potential energy, no change in kinetic energy. Just kind of looking at this little sketch here. Q in minus W out equals M dot times H out minus H in. All right. So if you divide both sides by M dot, that's where you get little w. That's called the work for an open system. And the work for an open system is going to have units kilojoules per kilogram or BTUs per pound. Just look at the units associated with this and you'll see kilojoules per kilogram or BTUs per pound mass. Textbook review. I'm going to try to chase you back to section 613. That chapter 6 had to do with calculating entropy changes and also analyzing reversible processes. And so notice here, this is a statement of the first law. Okay. And so what we're going to try to do is introduce the idea of reversible work, W dot over M dot, and that's going to be equal, based on the first law, Q dot divided by M dot plus H1 minus H2 plus minus the change in kinetic energy plus minus the change in potential energy. And so this is an uncomfortable for me statement of the first law, because in my world, I always start with Q dot in minus W dot out equals M dot times H2 minus H1 plus V2 squared minus V1 squared over 2 plus Z2 minus Z1 over G. So I find this to be a little uncomfortable, but it is certainly a valid statement of the first law. More reading, as you read down in section 613, you see that the reversible work is defined, W dot over M dot, is minus the integral of VdP plus V1 minus, sort of minus the change in kinetic energy, minus the change in potential energy from outlet to inlet. Okay. And so in the absence of changes in kinetic energy and potential energy, we can show that. So the book does a great job of showing that W reversible, the reversible work, W dot over M dot, for an open system, reversible process, is minus the integral of VdP. And the interesting thing to visualize then, how would you visualize minus the integral of VdP? Well, on a PV diagram, it is an integral, but see how you're integrating vertically. You're integrating vertically, dP, VdP. And so it's very important that you recognize as a young engineer that there's a difference between the work for a closed system, reversible process, integral of PdV, the work, W dot over M dot, reversible for an open system, minus the integral of VdP. Those are two different animals. And this is going to come into play for your pump work or pump power calculation. Okay, so now let's look at calculating reversible work for a pump. I just introduced this idea right out of your textbook. Work reversible for open system, steady state, steady flow, reversible process, minus the integral of VdP. Now for a pump, we're dealing with incompressible liquids. So V is a constant, specific volume is a constant. We can pull that out of the integral. Well, good. Even I can do this integral, the integral of dP. That's P, evaluated from 1 to 2. So simple. Work reversible equals minus P2 minus P1. So watch out for that pesky minus sign. So we'll move down to the next step. Work reversible pump is V inlet times P1 minus P2. So I've absorbed the minus sign into the parentheses. This is a very powerful, powerful expression for the reversible work for a pump handling an incompressible fluid. Okay. Evaluate V inlet as VF at T1. This is refresher. Remember that for any incompressible substance, the properties depend on the temperature of that substance, not the pressure. So we're going to evaluate V inlet as V sub F, saturated liquid, at T1. V sub F at T1. Okay. As a little extra, how would you calculate the outlet enthalpy of a pump? Now, you're going to be, in the pump analysis, this isn't going to be required, but when you start analyzing power plants, when you multiple pieces of equipment, this pump is discharging liquid to some other piece of equipment, and you're going to need to analyze that other piece of equipment, so you're going to need H2. So I'm going to show you how to do that. We'll start out with the statement of the first law for any open system, steady state, steady flow, one inlet, one outlet. First law, you shouldn't have to go to a formula sheet for this. You should know this in your head. Now for the pump. Pump's going to be considered adiabatic, fully insulated. So we'll strike it. Oh, we divide this by M dot. Divide everything, both sides by M dot to get little q in minus little w out equals H2 minus H1. Little q, it's going to be 0. Consider the pump to be fully insulated. So we can solve now for H2 as a function of H1 inlet minus W out. So what does your common sense tell you about H2? It should tell you, you should expect H2 to be a bigger number than H1 because W out is going to be a negative number. It takes power to drive a pump. It takes power to drive a pump. So I would expect H2 to be a bigger number than H1 since W out is less than 0. There's your crash course. So it's my hope that either you can look at those slides, replay the video to get up to speed on that, because it's hopeless. If you don't have a pretty good handle on all those fundamentals, it's sort of hopeless to have a good handle on what calculating pump power is all about. So let's look at an example. The test prep logo. If you were a student in my class, this is such a straight down the fairway question. A question like this would be on my test. Okay, absolutely. Determine the power required to operate a fully insulated pump that's handling water with a mass flow of 2 kilograms per second. Inlet conditions 100 kPa and 20 degrees C. That sounds a lot like tap water, doesn't it? 100 kPa, atmospheric pressure, 20 degrees C. Sounds like tap water temperature. Discharge pressure of 2.5 megapascals. That's pretty high pressure. Okay, that'll be a pretty high pressure delivery pump. And the pump efficiency is 80%. This is as straightforward as you can get for a pump analysis. All right, let's look at our sketch. We're going to start with a sketch. There's the schematic of a pump. Do you see how the schematic looks an awful lot like? It's supposed to depict what a real pump looks like, centrifugal pump. Here's our inlet conditions at state 1. Here's our outlet pressure at state 2. I'm showing the pump efficiency of 80%, and I'm showing work out of the pump. But I'm also, look how I'm depicting that I'm recognizing that the work out of the pump is less than 0. So on my sketches, I always show work out and I always show heat in. Now, why am I not showing heat in on my sketch? Because it's adiabatic. There's no heat going in, no heat transfer in. And remember, we've got a steady state, steady flow, open system with one inlet and one outlet. It's important then to draw a TS diagram. So for this, well, where's the vapor dome? Because we've got water, we're dealing with water. Well, for this, our tap water, 100 kPa and 20 degrees C, this is going to be to the left of the vapor dome because it's a compressed liquid. So if this had been a saturated liquid, this would sort of represent the vapor dome. But we're to the left of the vapor dome in the compressed liquid zone. So here's a line of constant pressure at 100 kPa. I'm also showing a line of constant pressure here, okay? Kind of like on the TS diagram, like a TS diagram to the left of the vapor dome. And I'm showing the isentropic process that we'll study first, 1 to 2I. And then I'm recognizing that state 2A has to be to the right of 2I because we've got no heat transfer. And so the entropy, since it's irreversible, the pump process is irreversible, we're going to be S2A is going to have to be greater than S2I. All right. So there is my TS diagram. As a reminder, the textbook calls this point 2S, and the textbook calls this point 2. And in my world, I like to think of this as 2I for 2 isentropic. And in my world, I like to think of this as 2A for actual, as opposed to just 2. This has helped me out a lot in my work life. Okay, so before we start putting pencil to paper, let's look at the solution approach. Ultimately, our last step is going to be calculating the pump power, because during our computations, we're going to be dealing with little w. We need little w actual in kilojoules per kilogram. We'll multiply by kilograms per second to get power. All right. So we're going to go to the temperature table to look up V1, which will be VF at T1. We will also look up H1 when we try to calculate the outlet enthalpy of the pump. That's going to be H sub F at T1. We're going to study the reversible pump. Reversible work is V times P1 minus P2. Just sort of derive that from class notes. We will apply pump efficiency to find the actual work, W actual. And once we found W actual, we'll apply the mass flow to get the power needed to drive the pump. Okay, so here we go. We'll go to our temperature table to look up V sub F. And don't forget, look at the column heading for specific volume in SI. We've got to slip our decimal place 3 places. And so our specific volume at 20 degrees C is 0.001018 cubic meters per kilogram, not 1.0018. It's a common undergraduate student mistake that's critical in pump power calculations. And also we'll write down H sub F. The inlet enthalpy of the pump is 83.96. Okay, so let's find the reversible work for the pump. It's V inlet times P1 minus P2. We just wrote down the specific volume. We've got our, pressures. Don't forget, if you stay in kPa, that's going to give you the correct units of kilojoules per kilogram. You should have been able to work through the units of that, say, in the second week of class. So recognize P2 is not 2.5, it's 2,500 kPa. 2.5 megapascals, 2,500 kPa, and that's going to give you negative 2.4 kilojoules per kilogram. Does that make sense? Does a negative number make sense? Yes. It takes power to drive the pump. I would expect a negative value there. Yes. Now to pump efficiency. I'm going to suggest that you should be able to write down pump efficiency, not from memory, but by figuring it out, and not by going to a formula sheet. You should be able to figure this out. Recognize that pump efficiency is always a number less than 100%. And in your mind, very quickly think, I've got two pumps. Which pump would it take less power? Will it take less power to pump my fluid with a reversible and adiabatic process, or an irreversible and adiabatic process? Which would be less power needed? I think it's the reversible and adiabatic process, less power. And so you want to be able to plop down this definition of pump efficiency on your own. So we've got W reverse, it's a negative number, so I would expect W actual to be a more negative number, So W actual is W reversible divided by pump efficiency, A to pump. All right, so let's do the numerics. We just found work reversible. We've got 80% pump efficiency, and so the actual work needed to pump the fluid is -3 kilojoules per kilogram. Does that make sense? Well, negative, yes, and it's more negative. It's more negative than the reversible. It all makes sense. We will apply our mass flow, 2 kilograms per second to kilojoules per kilogram to get -6 kilowatts. So in a test situation, to provide great clarity on what you're trying to say as an engineer, write out the sentence. The pump requires 6 kilowatts of power. The pump requires 6 kilowatts of power. Okay, the little extra bonus. How do we calculate H2 actual? How do we calculate the actual outlet enthalpy of the pump? We use the first law. W actual, Qn minus W actual equals H2 actual minus H1. Well, remember there's that minus sign there. So W actual is H1 minus H2A. Solve for H2 actual. It's H1 minus W actual. This is going to be a negative number. So H2 actual is going to be a bigger number than H1. And sure enough, there it is. H2 actual is 86.97. That's H2 actual. Got it? All right, let's do a second pump problem just for practice. And the other part is, let's do it with English units, because you're going to be faced with calculating pump power needs in English units. It's going to be horsepower, BTUs per hour, BTUs per pound, cubic feet per pound mass, all those units, the English, and they're tougher than SI units. Yeah. Okay, here we go. Determine the power required to operate a fully insulated pump handling water with a volumetric flow rate of 600 GPM. Inlet conditions 14.7 psia and 60 degrees F. Discharge pressure 150 psia. And pump efficiency 80%. Now let's see what's different about this problem. Here we're given volumetric flow rate, 600 GPM, gallons per minute, 600 gallons per minute. So the first thing, one of the first things we'll need to do is transform volumetric flow into mass flow. So we're going to need the specific volume, aren't we? Specific volume. And we're going to need to get that anyway. Okay, and let's see, what else do we, 14.7 and 60 degrees F. That's ambient conditions. That's a bucket of water. 14.7 atmospheric pressure, 60 degrees F. Tap water. So there we go. And discharge pressure, 150 psi. That is very much representative of processed water that's delivered industrially or even sometimes at the street. Okay, so here is our sketch. It's going to look very similar to the SI, just changing input around. We don't need to belabor that. Remember, W pump less than 0. My little practice of always showing output power, but then explaining that I expect it to be a negative number. TS diagram, we're to the left of the vapor dome. We're in the compressed liquid region, incompressible fluid. Okay, let's look quickly at our approach before we start crunching numbers. Our last step is going to be applying the mass flow rate to W actual. We're going to need to keep units, very careful with units on this. We're going to need V1, evaluate temperature table. We're going to need to transform our volumetric flow in gallons per minute into mass flow in pounds per second. I'm going to show you how we're going to use conversion factors to do that, as well as specific volume. We're going to transform pressure units from pounds per square inch immediately into pounds per square foot. That is a key to success. It's just flat doing that. It's right out of the box. Transform pressure units into pounds force per square foot. Then we're going to study the reversible pump. Reversible pump work, V times P1 minus P2. And we're going to get units. If you look quickly at the units, you're going to see that you're going to get units of foot-pounds force per pound mass. And we're going to immediately transform those units into BTUs per pound mass. We will apply the pump efficiency to find little W actual, and then we'll multiply little W actual by the mass flow rate to get the output power. And then we're going to still have units conversion. We're going to have to transform our W dot, whatever units we come up with, into horsepower. And it's easy, but you have to know the conversion factor. All right, so let's get started on the numerics. We're going to go to our temperature table, pump inlet 60 degrees F, and we're going to write down the specific volume as 0.01604 cubic feet per pound mass. And we'll also write down H1 is H sub F at 60, 28.08 BTUs per pound. Okay, so let's transform volumetric flow rate into mass flow rate. Let's see. Volumetric flow is equal to m dot times little v inlet. Pounds per second times cubic feet per pound mass is going to be cubic feet per second. Okay, and so m dot in pounds per second is going to be volumetric flow in cubic feet per second, divided by v inlet, cubic feet per pound mass. All right, so we've got some conversion. We need cubic feet per second, and we've got gallons per minute. So let's write down our conversions. Okay, we've got 600 GPM given. We'll go and look up a conversion to see there's 0.13368 cubic feet in 1 gallon. Like a gallon of milk is 1.13368 cubic feet. Okay, so we will get our unit straight and see that the volumetric flow is 80.208 cubic feet per minute. 80 cubic feet per minute. Okay, so I multiply these together to get 80 cubic feet per minute. Well, I need cubic feet per second, So there's 60 minutes in a second. So I'm going to divide 80 by 60 seconds in a minute to get 1.3368 cubic feet per second. So that's my volumetric flow rate that I need. Mass flow rate is the volumetric flow divided by V1, cubic feet per pound mass. And so I've got a mass flow rate of 83.34 pounds mass per second going through the pump. Mass flow rate going through the pump, 83 pounds per second. Now we got the reversible work of the pump. Okay, so we just got m dot. We're going to put that off to the side. Reversible work now. Okay, V times P1 minus P2. Got to get my units straight. Let's see. 312.5. I just do the math. V and P1 and P2. Oh, gosh, did I show my pressure? So I'm sorry. I have to get those pressures converted to pounds per square foot, and I haven't shown it on the slide, but I have on the solution. Okay. Conversion, 778 foot-pounds force is 1 BTU. Okay. And so I'm going to take 312 divided by 778 to get my reversible work is negative 0.402 BTUs per pound mass. let's see, since I didn't show my work for P1, what's the pressure at P1? 14.7. I would take 14.7 pounds per square inch, multiply by 144 to get pounds per square foot. Okay, so we've determined work reversible for the pump. We recall the definition of pump efficiency. So little w actual is going to be the reversible work divided by the turbine efficiency. And so the actual work is negative 0.502 BTUs per pound mass. Negative 0.502 BTUs per pound mass. Okay, got it. Does it make sense? Yeah, it's a bigger negative number. All right, so now we're going to pay close attention to units. Okay, I've got W actual negative 0.502 BTUs per pound mass. I've got M dot 83.34 pounds per second. So I've got a W dot actual. The actual power is negative 41.85 BTUs per second. Ugh. Now, I'm going to do a little work. I'm going to go to the back of the book and I'm looking for horsepower. And I see I have a conversion here. 1 horsepower is 2545 BTUs per hour. So it makes sense that I need to transform BTUs per second into BTUs per hour in order to use this conversion. So that's what I did. 3,600 seconds in an hour. So I've got 3,600 times negative 41.85 to get this huge number of BTUs per hour. I've got a conversion of 2545 BTUs per hour equals 1 horsepower. Okay, so now I can visually see what I need to do. I need to take this big number divided by 2545 to get negative 59.2 horsepower. And so if it's a test, I'm going to write out in a sentence, the pump requires 59 horsepower to operate. And that's a good statement of pump power required. You see how these units, boy, you have to be very careful with these units to get things straight. Very tough to do it all in one step. In my work, I have found that if I do things step by step by step, I can keep myself straight. So then the little value add, let's find H2 actual. What's the actual outlet enthalpy of that pump? Well, we'll use the first law. Q is 0 minus W actual. Q minus W actual equals H2 actual minus H1. We're going to take care of that minus sign. So W actual is H1 minus H2A. That's a statement of the first law. Steady state, steady flow, open system. So H2 actual is H1 minus W actual. It's going to be bigger because W actual is a negative number. So H2 actual is 84.46. And look at this, look at this. These units are incorrect. So copy and paste killed me. Didn't do me any favors again. This should be BTUs per pound mass. This should be BTUs per pound mass. And this should be BTUs per pound mass. So please forgive the typo. I'll try to go correct that on my PowerPoint slides, but we're going to let that fly here on the video. So do recognize my blunder in units. Okay, so let's recap. Pump analysis approach. What did we do? We studied the reversible process to get W reversible. We applied pump efficiency to get W actual. Okay. We were careful with units, determine the actual process results using the first law for steady state, steady flow. Okay. And then finally, if you need to find the outlet enthalpy, use the first law to determine the pump outlet enthalpy. Okay, well, please pardon me for that blunder on the slides of the units in SI, those final units. I'm going to go try to correct that on the PowerPoint, but I do hope that this has helped give you a better understanding, a little better experience in calculating the power requirements for pumps.